40. Got differentiable function f of x plus h minus f of x equals 4x h plus 2h squared. And so that is true for all x. And ultimately, the question here is let f of 2 be 5. And we want to know what is the value of f of 1. Right? So, ultimately, if you look at the equation here, what do we notice about this top? Does it look familiar? That's the top half of the derivative, slope equation, if you will. Okay. All right. So, knowing that, then keep in mind if we factored an h out of this side, if we did f of x plus h minus f of x, and we factored an h out of the right side and we divided, we'd have 4x plus 2h here, wouldn't we? True? Okay. Alright. So ultimately, that means that this slope is equal to this expression right here. Okay? And keep in mind, this is the slope of f. True? And it's the slope of f between 2 points. Okay? And ultimately, if we were to take the limit of both sides as h approaches 0, what do we ultimately have on the left-hand side? This is the derivative of f, isn't it? And if we did the same thing on the right-hand side, we'd get 4x. Let h go to 0 on the left-hand side, we get 4x. So with that, knowing that the function, or the derivative here, we ultimately, it's just a differential equation problem then, isn't it? Recognizing that that's the derivative that we're given. And so therefore it would be 2x squared plus c would be the function. And if we plug in our 2, 5 that they gave us, 5 here and 2 here, we get negative 3 equals c. So we'd ultimately get y equals 2x squared minus 3. And then if we put a 1 in there, negative 1. And that would be letter B. Alright, so that would ultimately be an AB problem, just a definition of derivative. Pretty good problem, I don't think I've ever seen that before. So, I guess again, the key giveaway is that you should recognize that expression on the left as part of the derivative here, and you can notice that they both have an h in common on the right, so you'd ultimately get that slope on the left. Equate those two things with the derivatives. Yeah.
I have a question about that problem. So as you take the limit as h approaches 0,
Yep.
and it's, hold on, just figured it out. You got rid of that h, that can be divided by h.
Yeah, because this is 0 here.
Yeah.
It was h here and h squared here, so it would be in
Alright.
4x plus 2h
I see it now.
divided by h. What else? Okay.
41.
On 41, we have dy dx equals e to the x times y. We got y equals 3. When x equals 0, we want to know y equals. So ultimately, again, it's just a AB problem. So we go 1 over y dy, e to the x dx over here. We separate the variables. So separation of variables differential equation. And if we anti-differentiate, we get natural log of absolute value of y equals e to the x plus c. And if we put our initial condition in here, it's x is 0, so that means we'd have c on this side, ln 3 over here. So ultimately we have ln absolute value of y e to the x plus ln 3. Alright, so with that, the issue is, can we solve that for, once we find our c value there, can we find y? What are we going to do to get this ln out of here? Compose both sides with e. So we get y here. Now here we'd have e to the x plus ln 3. The algebra technique we want to use here when we have e to some addition argument is rewrite it as e to the x times e to the ln 3, which ultimately that whole thing right there is just 3. It'll be 3 e to the x. Right?
How does c equal ln 3?
We put a 0, 3 in there, didn't we? You see x is 0. Oh, you know what? Shoot, it's... Yeah, you're right. Sorry. Let me revise that. Yeah, again 0 here for some reason. So ultimately putting a 1 in here would give us c plus 1 equals ln 3, right? So if we subtract, we'd have, actually we'll have ln 3 minus 1 equals c. So let's redo that over here. So we have ln absolute value of y equals e to the x plus ln 3 minus 1. So we'll just start over again then. Thanks. Right. So now if we compose both sides with our e function, we're going to get y over here, and this is going to be e to the x plus ln 3 minus 1. Alright. And now if we put our we use our laws of exponents, we would have that. And of course the e to the ln 3 part, that's just 3. We'd have 3 e to the x. And then e to the 1 here, we could write e to the negative 1, we could write e to the 1 on the bottom. Okay. So either way we look at it, if we had e to the 1 on the bottom, if we wrote it like that, we can put these two together because they have the same base. Just have a subtraction of exponents. So it'd be 3 to the e to the x minus 1. And actually, no, they just left it like that, didn't they? So it should be letter E, is that what I said?
Yeah.
Good. Alright, so ultimately again, in general, just the general strategy here being a differential equation is we're going to separate variables. Okay? Differentiate both sides. Plug in the initial condition immediately and find C. And if we find C correctly, then we can do the rest of the algebra correctly. Okay? So once we find C, which is ln 3 minus 1, we can do that. And the key information here, we've had quite a few of these here in AB that when we have this situation where we have e to some addition or subtraction of powers, we can rewrite that with our laws of exponents as the base. And again, that works because if I have e times e, what do I do to powers if I have e times e? I add them, so ultimately I'm just unadding that, I'm just going backwards on that property. Same thing with the subtraction as well. Okay. What else? Let's sub 345. Jake.
44.
And 44, we have a graph shown here. And it says here that the graph shows a function f with a relative minimum at x equals 2. And it says the approximation of f near x equals 2 using a second degree polynomial, Taylor polynomial centered at 2 is given by the following. So that approximation for that curve we see looks like that ultimately. Alright. And the issue here is which of the following would be true about A, B, and C in terms of any of those being 0 or greater than 0, less than 0, and so on. Okay. Alright. So if we're going to use again a second degree polynomial to mirror this particular curve, remember that when you look at the curve itself, when we have a Taylor polynomial, and not faint down here, but ultimately if you have that Taylor polynomial near to the point in question, our curve that we have should be pretty close to what the curve shows in terms of y values and so on. But ultimately, we've got a second degree polynomial, so it's not going to behave like this over here, but it would be kind of a parabola essentially. That would mirror the behavior around the minimum. Agreed? So let's see if that helps us knowing what that picture must look like. Again, just real briefly, our picture, our parabola maybe looks something like that. If this is our cubic and looks like a cubic, maybe not a cubic, but either way, our parabola should look like this. So based on the fact that we do have a minimum at that point at 2, okay, what would that tell us about C? Remember, this is a equation for this parabola essentially that I drew here, isn't it? So what would that be said about C? Would have to be what? It would have to be greater than 0. It opens up, doesn't it? Okay. So that means C would have to be greater than 0. Ultimately, that rules out B and C. All right. Now, what about B and A here? What could be said about B and A? We know that the y value here at 2 would have to be. Keep in mind that ultimately, if this has a think about this. If this picture has a derivative of 0 at 2, then our polynomial should have a derivative of 0 at 2 as well, shouldn't it? So if I were to find the derivative of this expression, we'd have simply b, and then we'd have plus 2c x minus 2 to the 1, if you will. True? So keeping in mind that this would have to equal 0 at 2. True? So if this equaled 0 at 2, if I plugged a 2 in there, this whole thing would be 0, wouldn't it? So in order for this to equal 0, what would have to be said about b? Wouldn't b have to be 0 as well? Okay. So 2 down. Alright, does that rule out any of the other ones? Looks like A is still in, and E is still in. So ultimately it's this A value here. So if this is the A value, okay, keep in mind that the A value here is going to be the y-intercept of our parabola, isn't it? And based on our picture in the plane, if we were to draw a curve that kept going in that same pattern, okay, wouldn't the y-intercept not be positive? Positive or not positive? If we were to draw, keep in mind we're not talking about the y-intercept of the actual curve. Okay, we're talking about the y-intercept of our parabola. Okay. So if I were to draw this, keep in mind that here's your x and y-axis, somewhere like this. Ultimately, if I kept going, wouldn't this have to be a y-intercept of somewhere in the positive y values? So ultimately, actually. Oh, they got negative, don't they? Let me think about y. Hold on a second. Let's see. So if you got modeling that equation with this parabola. Yeah, you're right. You're right. That's exactly why. Because ultimately, again, if we had known an equation for this function, we would have started out with f of 0, wouldn't we? Okay. So ultimately, you're right. That a should be equal to f of 0, because when we build that Taylor polynomial in the first place, that first coefficient is f of 0. So good call. So ultimately, f of 0 here we can see is negative 6 or whatever it may be. So therefore, a would be less than 0. Therefore, a. Good one. All right. Other questions? What else? What else? 43, we have a region R that's enclosed in the by the coordinate axes in the graph of y equals k times x minus 5 all squared. K times x minus 5 all squared, keep in mind, would have a vertex of 5, 0, it's just 5 to the right, because that's in and we don't know how fast this goes up or down because we don't know k, but ultimately, it's going to look something like that. Okay. And the question here says, when this region is revolved around the x-axis, a solid is formed that has a volume of 2,500 pi cubic units, and you want to know what is the value of k. So, again, the coordinate axes and the curve, ultimately the curve, it would look like something like this then, wouldn't it? With this being our region. Okay. So if we took a vertical slice, which we can do because it's the equation we're given is in x, and we revolve that around the x-axis, we're ultimately going to get what shapes? We're ultimately going to get a disk. So we know that we'll go from 0 to 5 for our integral here, and the disk is going to be pi times r squared. R would be k times x minus 5 all squared, dx, thickness of each disk. And we know ultimately that is to equal 2,500 pi. True? Alright, so you can find the antiderivative of this any way you want to, but I would suggest that making it a power function would probably be as easy as anything, I guess. You don't have to worry about the substitution part here, but ultimately the pi's, we could get rid of the pi's at this point and just go, we did, in here we'd have x squared minus 10x plus 25. So we'd have kx squared minus 10kx plus 25 all squared dx equals 2,500. And again, just divided both sides by pi to get the pi out of our hair, basically. And then from here, we could, again, we can just use the power rule here as long as we just multiply that out. So it might be tedious to multiply out and get those 9 terms in there, but ultimately we're still just after the antiderivative here. So if we did that, we'd get k squared x squared, and then this times, ultimately again, just rewrite it twice if you need to. Yeah.
Can we take the k out of the integral since it's a constant?
Actually you could. However, you'd have to have k squared here though. Yeah, you're right. That'd be way easier. Sorry. Can't clear that here. Ultimately, you'd have k squared out on the outside here though, because when you put that in there as your radius, okay, this would be k squared, and this would be x minus 5 to the 4th. Okay. So then if you just go x minus 5 to the 4th as your integrand, I forgot we're in the calculator part too, so that makes it a lot easier to do all that multiplying. Alright, so ultimately that should be a true sentence because again k is a constant multiple, so therefore it could come out. But again, k can't come out because it's being squared, so it's got to square this and square this, which makes those two. We can take the k squared out. And then from our calculator, again, save time since we're in the calculator part, we can just calculate that and get what? Anybody have it? 625. And if we divide that into 2,500 divided by 625, much? 4. And so conveniently our answer is 2. Keep in mind here, we might have an option between plus and minus 2. Why would it be 2 and not negative 2? How would we know? The original function, if this was a negative 2, wouldn't this thing open down? And because it says k greater than 0. Okay. All right, others. On 42, we have this g function. It's defined as an integral function. So our g function here is, let's see, integral from 3 to x of 5 plus 4 t minus t squared 2 to the negative t dt. Alright, so with that being our g function here defined by this integral, we have to decide here which of the following statements about g must be true. So the first part is asking about increasing, and then the other issue is how about the value of g of 7? Is it less than 0 or is it greater than 0? So keeping in mind here that that the increasing and decreasing part is going to come from the derivative of g. So if we do g prime here, g prime is just going to be 5 plus 4x minus x squared times 2 to the negative x. Integrand evaluated at the upper limit. And so if we want to tell if that's positive, we can graph it. It'd be quickest approach since we have a calculator on this problem. And ultimately we're only concerned about 3 to 5 and 5 to 7, so I'll just keep it on 0 to 10 like I had for a problem that we had earlier. Alright, so I'm going to zoom in on that a little bit here just so we can see the what happens here. It looks like it's at 5 that the action's taking place here. We can do the 0 command on that if we want to. But bottom line here is that the derivative is positive before we get to 5 and negative after. True. So what could be said about number 1? It's increasing on 3 to 5. The derivative is positive on 3 to 5, isn't it? So wouldn't that be true? 5 to 7, the derivative is negative, so therefore that's not true. And then what about g of 7 finally? Well, g of 7, if we just put a 7 in here, go the area from 3 to 7 of our function, let's see what happens. So we got, if you already have that typed in your y equals, I'm pretty sure you can just type in y1, I believe. You don't have to retype that thing. And it looks like it's 0.56, so on. So therefore it should be what? I guess it would be A then, because that 3 would be wrong then, huh? It's positive there. So 2 and 3 are both no good, so 1's the only good one. So therefore it should be A. Alright, so AB problem, ultimately be just a fundamental theorem problem.